On Jupiter's moon Io, the ground is alive. Mountains rise and collapse, rivers of molten rock flow across plains, and volcanoes erupt with a power far beyond anything on Earth. Yet this is not a planet, it is a moon, the most volcanically active body in the entire solar system. Beneath its colorful surface, a world of extreme energy and constant change is at work. Heat radiates from deep within, sculpting landscapes in real time. Lava fountains shoot hundreds of kilometers into space. Plumes of sulfur and silicate dust drift across the sky, carried by winds that would flatten any human-made structure in seconds. Io has been known for centuries, but it was only in 1610 when Galileo Galilei first observed Jupiter's moons through his telescope that its existence was documented. For hundreds of years, it remained a distant, twinkling point of light. Little could anyone imagine the violent world hidden beneath that serene appearance. The key to Io's extreme activity lies not in sunlight, but in gravity. Jupiter, the largest planet in the solar system, exerts a gravitational pull so strong that it stretches and squeezes Io with every orbit. This tidal heating generates intense friction inside the moon, melting rock and fueling volcanoes. Europa and Ganymede, its neighboring moons, participate in an orbital resonance that keeps Io in constant motion, amplifying these internal stresses. Every eruption, every lava flow, every shifting sulfur deposit is a result of this cosmic dance. In 1979, the Voyager spacecraft provided humanity's first detailed glimpse of Io. The images revealed a landscape unlike anything on Earth. Vast plains painted in yellow, red, and orange, shaped by sulfur compounds and molten rock. Volcanoes like Pele and Loki Patera were already active, indicating a moon in perpetual transformation. Scientists realized immediately that Io was not just another moon, it was a laboratory of extreme planetary processes, unlike anything seen before. Io's surface is alive with activity. Lava lakes form, drain, and refill. Mountains rise and crumble. Rivers of molten silicate carve valleys as they flow. Plumes of sulfur dioxide and other gases erupt into space, sometimes reaching heights higher than the Earth's atmosphere. These eruptions are not isolated events, they are continuous, a constant reshaping of the landscape. The heat on Io is extreme. Lava can reach temperatures above 1600 degrees Celsius, hotter than any volcanic eruption on Earth. These eruptions are driven entirely by tidal forces, unlike Earth where most internal heat comes from radioactive decay. Every plume, every lava flow, every glowing surface patch is a reminder of the immense energy generated by Jupiter's gravity. Radiation adds another layer of danger. Jupiter's magnetosphere accelerates charged particles that bombard Io, producing radiation levels thousands of times higher than a lethal dose for humans. Spacecraft that venture too close must rely on heavy shielding, precise trajectories, and brief encounters. Galileo, which orbited Jupiter in the late 1990s and early 2000s, experienced gradual radiation damage despite extensive precautions. Juno, currently observing Jupiter and its moons, carries sensitive instruments inside a titanium vault, allowing it to survive short exposures to this harsh environment. Io's atmosphere is almost negligible, a thin veil of sulfur dioxide, yet it plays a crucial role in the moon's chemical and geological processes. Ejected materials interact with Jupiter's magnetic field, creating auroras and feeding a plasma torus that encircles the planet. This demonstrates that Io is not merely a passive satellite, it actively shapes the space environment around Jupiter. Volcanoes on Io are unpredictable. Some regions remain active for decades, while others erupt without warning. Hotspots shift, lava lakes drain and refill, and mountains collapse. Every eruption defies expectation, highlighting the complex interplay between tidal heating, orbital resonance, and internal composition. This unpredictability challenges our models of planetary geology and provides insight into how extreme environments operate. Io's advantages go even further. Material ejected into space contributes to a ring of particles, some of which are trapped by the planet's gravity, feeding radiation belts and creating visible auroras. The Moon's volcanic activity, gravity, and chemical emissions demonstrate how even a small moon can influence an entire planetary system. For decades, scientists could only speculate about Io's interior. Observations from Galileo and Juno suggest a partially molten mantle, continuously replenished by tidal heating. The surface, with its mountains, plains, and lava lakes, offers a direct window into these processes. By studying Io, researchers gain insight into extreme planetary physics, volcanic dynamics, and the chemistry of high-temperature environments. Io's mountains are extraordinary. Some rise nearly 17 kilometers above the surface, taller than Mount Everest. Unlike mountains on Earth, they are composed of sulfur-rich rock, shaped by internal pressures and volcanic activity rather than tectonic plate collisions. They appear jagged and unstable, often collapsing or erupting in molten flows. Every peak and valley tells a story of energy, pressure, and chemical transformation. The lava lakes of Io are equally remarkable. Loki Patera, one of the largest, spans nearly 200 kilometers. It periodically drains and refills, creating thermal pulses visible from Earth-based telescopes. These cycles provide a rare opportunity to study geological processes in action, showing how extreme environments behave over time. Observing Io is not without risk. The radiation alone would be fatal to unshielded humans. Temperatures vary drastically. Surface areas in shadow plummet below -143 degrees Celsius, while active lava reaches over 1,600 degrees Celsius. A spacecraft must navigate carefully, balancing proximity for observation with exposure risk. Yet, despite these dangers, Io continues to fascinate scientists. Its intense volcanic activity offers a glimpse into planetary processes that cannot be replicated on Earth. Its chemical and physical interactions reveal the influence of gravity, resonance, and extreme heat on a celestial body. Every eruption, every plume, every shift in its surface contributes to our understanding of how moons and planets evolve. Io also provides a model for understanding exoplanets. Many planets outside our solar system are tidally heated or volcanically active. By studying Io, scientists can predict how these distant worlds behave, what their surfaces might look like, and how internal energy shapes their evolution. This makes Io not just a curiosity, but a key to unlocking knowledge about planetary systems across the galaxy. For decades, Io has been observed, mapped, and analyzed. Each mission, Voyager, Galileo, and Juno, has revealed new details. Lava temperatures, plume heights, volcanic cycles, and surface composition all contribute to a picture of a world in constant motion. The Moon challenges assumptions about planetary stability, volcanism, and chemical dynamics. Io is a world of extremes: fire and sulfur, lava and ice, radiation and gravity, constantly reshaping itself under the watchful pull of Jupiter. It is a laboratory of cosmic forces where every eruption tells a story of energy, chemistry, and celestial mechanics. This is Io, a moon more dynamic than any other, a place where the universe shows its power and complexity in the most visible way. Every plume, every lava flow, every mountain and valley is evidence of a world alive with energy, forever changing and endlessly fascinating.